Welcome! In this session, we'll explore problem number 1135, connecting cities with minimum cost. This problem falls under graph theory and optimization, and the goal is to find the minimum cost required to connect all cities. Let's dive into the problem and its solution. In this problem, we are tasked with connecting a number of cities, labeled from 1 to n, in such a way that the total cost of connecting them is minimized. The connections between cities are represented as a list of three integers, city 1, city 2, and the cost to connect them. Importantly, these connections are bidirectional, meaning the cost to connect city 1 to city 2 is the same as connecting city 2 to city 1. The goal is to determine the minimum cost required to ensure there is a path between every pair of cities. If it is impossible to connect all the cities, the output should be -1. This problem is fundamentally about finding the minimum spanning tree, or MST, of a graph. Here, the cities act as nodes, and the connections are weighted edges of the graph. The MST ensures we connect all nodes with the minimum total weight while avoiding any cycles. The output for this problem is a single integer that represents the minimum cost needed to connect all the cities. If it is impossible to connect every city, meaning some cities remain isolated, we return -1. Let's look at some examples to better understand the problem. In the first example, we have 3 cities and 3 possible connections with their respective costs. Connecting city 1 to city 2 costs 5, connecting city 1 to city 3 costs 6, and connecting city 2 to city 3 costs 1. The task is to determine the minimum total cost to connect all 3 cities such that there is at least one path between every pair of cities. To solve this first example, we can connect city 1 to city 2 at a cost of 5, and then connect city 2 to city 3 at a cost of 1. These two connections ensure that all 3 cities are connected, and the total cost is 5 plus 1, giving us the minimum cost of 6. Now consider a second example with 4 cities and 2 connections. Connecting city 1 to city 2 costs 3, and connecting city 3 to city 4 costs 4. Here, it is clear that no matter how we try to use the given connections, there is no way to connect all 4 cities. Specifically, cities 1 and 2 are completely isolated from cities 3 and 4. Therefore, the output in this case is -1, indicating that it is impossible to connect all the cities. In the third example, we have 5 cities and several connections with varying costs. To achieve the minimum cost, we can connect city 1 to city 2 at a cost of 1, city 1 to city 3 at a cost of 2, city 1 to city 4 at a cost of 3, and city 1 to city 5 at a cost of 4. By using these connections, all cities are connected with a total cost of 1 plus 2 plus 3 plus 4, which equals 10. This demonstrates how we can strategically select connections to minimize the overall cost while ensuring every city is part of the network. There are a few important constraints and edge cases to keep in mind for this problem. The number of cities, n, can go up to 10,000, and the total number of connections can be as large as 200,000. Additionally, the cost of any connection is bounded between 1 and 100,000. Since the graph may be disconnected, it is possible that not all cities can be connected, in which case the output should be -1. Some edge cases to consider include when the graph is disconnected, as we saw earlier, or when there is only one city, in which case the cost is 0 since no connections are needed. For large, densely connected graphs, the solution must handle a high number of edges efficiently. Lastly, the algorithm must adhere to the principles of a minimum spanning tree, ensuring no cycles are introduced when connecting the cities. These considerations will guide how we approach and solve the problem efficiently. To solve the problem of connecting cities with the minimum cost, we first considered a brute force approach. The intuition here is to explore all possible combinations of connections and identify which subset forms a spanning tree that connects all cities at the lowest cost. However, generating all subsets of connections is computationally expensive, with a complexity of O(2 to the power of m, where m is the number of connections. Additionally, checking if a subset forms a spanning tree requires O(n²) operations. This makes the brute force method impractical for even moderately sized inputs due to its exponential search space. Instead, we turn to Kruskal's algorithm, a greedy approach that is well suited for this problem. By treating the task as finding a minimum spanning tree, MST, Kruskal's algorithm sorts the connections by cost and adds edges to the MST only if they connect previously unconnected components. Using a union-find data structure, we efficiently track connected components and stop once the MST contains n1 edges, where n is the number of cities. This approach has a much better complexity of O(m*log m, making it both efficient and straightforward to implement, which is why it was chosen as the preferred method here. Another viable option for solving this problem is Prim's algorithm, which also takes a greedy approach to building the MST. The key difference is that Prim's algorithm grows the MST one node at a time, always adding the smallest edge that connects a new node to the existing tree. To implement this, we use a priority queue to keep track of the smallest edges available for extension. Starting from any arbitrary node, we repeatedly add the smallest edge that connects a new city until all cities are connected. This method has a time complexity of O(m*log n when using an adjacency list and a priority queue. While Prim's algorithm is efficient and works well for this type of problem, it can be slightly more cumbersome to implement when the graph is given in edge list format, as we have here. Therefore, while it is a strong alternative, it wasn't chosen for this specific scenario. The chosen strategy for this problem is Kruskal's algorithm. It is particularly well suited because the edge list input format aligns naturally with Kruskal's approach. By sorting the edges by cost and using the union-find data structure, we can efficiently construct the MST while guaranteeing correctness. The key insight here is recognizing that the problem can be reduced to finding an MST, and sorting edges by cost ensures that we always take the globally optimal path. When comparing Kruskal's algorithm to Prim's, we see that while both are efficient, Kruskal's simplicity and compatibility with the edge list format make it the better choice. Prim's algorithm, on the other hand, would be more advantageous if the graph were represented as an adjacency list or matrix. In terms of complexity, Kruskal's O(m*log m is competitive, and sorting edges is straightforward. Given these considerations, greedy MST algorithms like Kruskal's are the only practical choice for this problem, making it the ideal strategy for connecting cities with minimal cost. The problem we're solving focuses on connecting all cities in a network with the minimum possible cost. Each connection between two cities has an associated cost, and our goal is to find a subset of these connections that ensures all cities are connected, forming a spanning tree, while minimizing the total cost. To approach this, we start by representing the cities and their connections as a graph. Here, the cities are nodes, and the connections between them are edges, each defined by the two cities it connects and the cost of that connection. Once this graph representation is established, the brute force approach involves generating all possible subsets of the edge set. This essentially means considering every possible combination of connections between cities to explore all potential solutions. Each subset represents a possible way to connect the cities, and we'll evaluate whether these subsets are valid and their associated costs in the subsequent steps. Now that we have all subsets of edges, the next step is to filter out the valid ones. A valid subset must form a spanning tree, which means it must contain exactly n1 edges if there are n cities, and it must connect all cities without leaving any disconnected components. To confirm connectivity, we can use graph traversal algorithms like depth-first search or breadth-first search. Once we identify the valid subsets, we calculate the total cost for each by summing up the costs of the edges in the subset. We then maintain a variable, initialized to infinity, to keep track of the minimum cost observed so far. If a valid subset has a lower total cost than the current minimum, we update this variable. At the end of this process, the value stored in the variable represents the minimum cost required to connect all cities, which becomes our final result. The brute force method guarantees that we explore every possible combination of connections, ensuring that the optimal solution, or the minimum spanning tree, is included in our search space. However, the trade-off is its computational complexity. Generating all subsets of edges has a time complexity of O(2 to the power of m, where m is the number of edges. For each subset, we perform a connectivity check, which takes O(n plus m) time using DFS or BFS. This results in an overall complexity of O(2 to the power of m*n plus m, which grows exponentially and becomes impractical for large graphs. While this approach is useful for small graphs and educational purposes, it has severe limitations for larger datasets where efficiency is critical. The exponential growth in complexity makes it infeasible for real-world applications with substantial numbers of cities and connections. To implement the brute force approach effectively, we rely on specific data structures. First, we use an adjacency list to represent the graph. This structure is both space-efficient and supports efficient graph traversal operations like DFS or BFS. For storing subsets of edges, we can use arrays or bitmasks to represent each subset compactly. Additionally, during the connectivity check, we maintain a Boolean array called visited to track which nodes have been visited, ensuring that we can accurately determine whether all cities are connected. These data structures are critical for efficiently handling the operations required in the brute force approach, even though the overall algorithm remains computationally expensive. Given the limitations of the brute force approach, optimized algorithms like Kruskal's or Primps are often preferred for solving this problem in real-world scenarios. Both are greedy algorithms designed to compute the minimum spanning tree efficiently, with a time complexity of O(m log m). These algorithms prioritize efficiency and are well suited for larger graphs. Additionally, even within the brute force approach, we can implement early pruning techniques to skip subsets that contain more than n1 edges or subsets that cannot possibly connect all cities. While the brute force method is valuable for educational purposes and for testing small graphs, Kruskal's and Primps algorithms are the practical choices for larger and more complex networks where computational efficiency is essential. To tackle the problem of connecting cities with the minimum cost, we start by creating a graph representation using an adjacency list. This helps us organize the data where each city is a key, and its value is a list of tuples representing neighboring cities along with the cost to connect to them. We initialize the adjacency list for all cities from 1 to n, and then populate it with the given connections. Each connection specifies 2 cities and their corresponding cost, so we add this information for both directions since the graph is undirected. Next, we set up a priority queue, also known as a min heap, to guide our traversal of the graph. We begin with city 1 and an initial cost of 0, which we push onto the heap. A set is used to keep track of visited cities, ensuring we don't process the same city multiple times. We also initialize a variable, total_cost, to accumulate the cost of the connections as we proceed. The main part of the algorithm is a loop that continues as long as there are cities to process in the heap and not all cities have been visited. Within the loop, we extract the city with the smallest connection cost. If the city has already been visited, we skip it to avoid redundant work. Otherwise, we mark it as visited, add its cost to the total, and then inspect its neighbors. For each neighbor, if it hasn't been visited yet, we push it onto the heap along with the cost of the edge connecting it to the current city. For neighbors that haven't been visited, we push their connection cost and city number onto the heap. This ensures that the priority queue always maintains the edges with the smallest cost at the top, allowing us to pick the most cost-effective connections as we build our minimum spanning tree. Once all cities have been processed, we check if the number of visited cities matches the total number of cities, n. If they do, it means we've successfully connected all cities, and we return the total_cost. However, if not all cities are reachable, the graph is disconnected, and we return -1 as specified in the problem. This approach ensures that we find the minimum cost to connect all cities, provided it's possible, using a greedy algorithm based on Primps' minimum spanning tree method. Here, we start by importing necessary libraries like java.util** to handle data structures such as maps, lists, and priority queues. In the minimum cost method, our goal is to determine the minimum cost to connect all cities. First, we create an adjacency list to represent the graph, where each city is a key, and its value is a list of neighboring cities along with the cost of connecting to them. This is done by iterating through each connection and adding both directions since the graph is undirected. Next, we initialize a priority queue to store edges based on their costs, starting with city 1 and a cost of 0. A set called visited keeps track of cities that are already part of the minimum spanning tree, and we initialize total cost to 0, which will accumulate the cost of connecting the cities. The while loop runs as long as the priority queue is not empty and we haven't visited all cities. At each iteration, we extract the edge with the smallest cost from the priority queue. If the city from the extracted edge is already visited, we skip it to avoid cycles. Otherwise, we add the city to the visited set and update the total cost by adding the edge's cost. Then, we iterate through all the neighboring cities of the current city. For each neighbor, if it hasn't been visited yet, we add it to the priority queue along with the cost of the edge connecting it. This ensures that we always prioritize the cheapest edges first. Finally, after the loop, we check if all cities are connected by comparing the size of the visited set to n. If all cities are connected, we return the total cost. Otherwise, if some cities remain disconnected, we return -1 to indicate that connecting all cities is not possible. In this example, we have 3 cities and 3 connections with their respective costs. To find the minimum cost to connect all cities, we start by building an adjacency list to represent the graph. For City 1, we see it connects to City 2 with a cost of 5 and to City 3 with a cost of 6. Similarly, we list connections for Cities 2 and 3. Next, we initialize a min heap with a starting point of cost 0 for City 1, an empty set to track visited cities, and a total cost initialized to 0. In the first iteration, we pop the smallest cost from the heap, which is 0 for City 1. We mark City 1 as visited and add its neighbors, Cities 2 and 3, with their respective costs of 5 and 6, to the min heap. In the second iteration, the smallest cost in the heap is 5 for City 2. We pop it, visit City 2, update the total cost to 5, and add its unvisited neighbor, City 3 with cost 1, to the heap. In the third iteration, we pop the smallest cost from the heap, which is 1 for City 3. After visiting City 3, we add it to the visited set and update the total cost to 6. At this point, all cities have been visited, so we stop the process. The final output is 6, which is the minimum cost required to connect all cities. In the next example, we examine a disconnected graph with 4 cities and only 2 connections. To begin, we construct the adjacency list. City 1 connects to City 2 with a cost of 3, while City 3 connects to City 4 with a cost of 4. With this setup, we initialize the min heap, visited set, and total cost in the same manner as before. The first iteration starts by popping the smallest cost, which is 0 for City 1. We visit City 1, add it to the visited set, and push its neighbor, City 2 with cost 3, into the heap. Next, in the second iteration, we pop the smallest cost from the heap, which is 3 for City 2. After visiting City 2, we update the total cost to 3. At this point, there are no more neighbors to add to the heap. Unfortunately, not all cities have been visited, which means the graph is disconnected, and it's impossible to connect all cities. As a result, the output is -1. Now, let's analyze a larger graph with 5 cities and multiple connections. We start by constructing the adjacency list. For instance, City 1 connects to City 2 with a cost of 2 and to City 3 with a cost of 3. Similarly, we list the connections for the other cities. With the adjacency list ready, we initialize the min heap, visited set, and total cost. In the first iteration, we pop the smallest cost from the heap, which is 0 for City 1. We visit City 1 and add its neighbors, Cities 2 and 3, with costs 2 and 3, respectively, to the heap. In the next iteration, the smallest cost in the heap is 2 for City 2. We pop it, visit City 2, and update the total cost to 2. We then add City 2's unvisited neighbor, City 5 with a cost of 10, to the heap. Moving forward, the smallest cost in the heap is now 3 for City 3. After visiting City 3, we include its neighbors, City 4 with cost 4 and City 5 with cost 10, in the heap. The total cost at this stage is 5. In the fourth iteration, we pop the smallest cost from the heap, which is 4 for City 4. Visiting City 4 brings the total cost to 9, and we add its unvisited neighbor, City 5 with a cost of 1, to the heap. Finally, in the fifth iteration, we pop the smallest cost, which is 1 for City 5. Visiting City 5 completes the process, as all cities are now connected. The total cost to connect all cities is 10, which is the output. This example demonstrates how the algorithm efficiently connects cities while minimizing the total cost. In this problem, the time complexity of the solution is determined by 3 main operations: building the graph, managing the priority queue, and iterating through the nodes and edges. First, constructing the graph as an adjacency list involves processing each connection in the input. If there are m connections, this step takes m time since we iterate over the entire list once. Next, we use a priority queue to manage the edges. Given n cities and m edges, each edge may be pushed into the heap at most once. The heap operations, whether pushing or popping elements, take log k time, where k is the heap size at a given moment. In the worst case, the heap can grow to store all m edges, leading to a total of O, m log m, time for these operations. These two components contribute significantly to the overall complexity.
Now, let's consider the main loop of the algorithm.
This loop continues as long as there are cities left to visit and the heap is not empty. In the worst-case scenario, we process all n cities and examine all m edges. For each edge, we check if the neighboring city has already been visited, which is an O(1) operation per edge. When we sum up the contributions of the graph construction, priority queue operations, and the main loop, we get O(m) for graph construction, O(m log m) for the heap operations, and another O(m) from the main loop. Combining these, the total time complexity of the solution is O(m log m), where m is the number of edges. This logarithmic factor comes from the heap operations, which dominate the overall runtime.
Let's now move on to the space complexity of the solution.
The memory usage is influenced by the graph representation, the priority queue, and the visited set.
For the graph, we use an adjacency list, which stores each edge twice, once for each direction.
With m edges in total, this requires O(m) space. The priority queue, or heap, can hold up to m edges in the worst case, adding another O(m) space requirement. Lastly, the visited set keeps track of the cities that have been processed. Since there are n cities, this set may grow to hold all n cities, which takes O(n) space. When we combine these factors, the overall space complexity becomes O(m plus n). This is quite efficient given the constraints of the problem, as it scales linearly with the number of edges and cities. To understand why this approach is efficient, let's compare it to a naive solution.
A brute force method might involve generating all possible spanning trees and calculating their costs.
This would be computationally prohibitive, with an exponential time complexity, as it requires generating all subsets of edges and ensuring connectivity.
In contrast, our optimized approach uses Prim's algorithm with a priority queue.
This reduces the time complexity to O(m log m), which is far more practical for large inputs. Similarly, the space complexity is reduced to O(m plus n), which is manageable within the problem's constraints. These optimizations make the algorithm suitable for real-world applications where efficiency is critical.
Finally, let's discuss the best, average, and worst-case scenarios for the algorithm.
In the best case, if the graph is already connected and the edges are sorted by cost, the algorithm processes nodes and edges with minimal heap operations. However, the time complexity remains O(m log m) due to the inherent cost of heap operations. In the average case, with random edge weights, the algorithm performs as expected with O(m log m) time complexity. In the worst case, all edges might need to be added to the heap and processed, but even then, the time complexity does not exceed O(m log m), as each edge is processed at most once. The logarithmic factor comes from the heap operations. Each push or pop operation takes O log k time, where k is the size of the heap. Since the heap size is proportional to the number of edges, the total heap operations scale with m log m. The linear factors, O, m, and O, n, come from iterating over edges and cities, but they are additive. Overall, this algorithm is both time and space efficient within the problem's constraints. One of the most common mistakes when solving this problem is misunderstanding the problem constraints. For example, overlooking edge cases like disconnected graphs, duplicate edges, or invalid inputs can lead to incorrect solutions. It's essential to carefully validate the constraints and ensure your algorithm accounts for edge cases from the start. Another common issue arises from the inefficient use of data structures. For sparse graphs, using an adjacency matrix might unnecessarily increase the space complexity, so it's better to use an adjacency list. Additionally, cycle detection is a critical part of algorithms like Kruskal's or Prim's. If the union-find structure is not implemented correctly, it can fail to detect cycles, causing incorrect results. Finally, overlapping or redundant computation can be a major inefficiency. For instance, recalculating the minimum edge repeatedly in Prim's algorithm can be avoided by using efficient data structures like heaps or incorporating memoization techniques where appropriate. Another important mistake to avoid is not accounting for edge weights properly. In Kruskal's algorithm, for instance, failing to sort edges by weight will yield suboptimal solutions. Now, when tackling these types of problems in interviews, it's crucial to recognize patterns. If the task involves connecting nodes or minimizing costs, it likely relates to minimum spanning tree algorithms like Kruskal's or Prim's. For undirected, weighted graphs, MST algorithms are key. However, if the graph is directed, shortest path algorithms such as Dijkstra or Bellman-Ford might be more applicable.
It's also a good idea to explain trade-offs between algorithms.
For example, Kruskal's is typically more efficient for sparse graphs because it processes edges directly, while Prim's shines in dense graphs when implemented with a priority queue.
Lastly, always be ready to handle edge cases during interviews. Scenarios like disconnected graphs, negative weights, or even single node or empty graphs should be part of your test cases.
It's helpful to explore related problems to deepen your understanding of these techniques. For example, LeetCode problem 1584, min cost to connect all points, and problem 1168, optimize water distribution in a village, are variations of minimum spanning tree problems.
Problem 261, graph valid tree, shifts focus to validating tree structures, which can involve similar union find techniques.
When considering alternative approaches, Prim's algorithm is worth mentioning for its use of a priority queue to repeatedly select the minimum edge, making it highly suitable for dense graphs.
Its time complexity is O, E plus V log V.
On the other hand, Kruskal's algorithm sorts edges by weight and uses union find for connectivity, making it better suited for sparse graphs with a time complexity of O, E log E. Boruvka's algorithm offers a less common but interesting alternative for adding edges in parallel batches. While not typically seen in interviews, it's a valuable approach in academic or theoretical discussions, especially when parallel computation is involved.
Understanding brute force approaches can also be insightful, even though they are highly inefficient.
Generating all subsets of edges to find the minimum spanning tree has exponential complexity, but it helps build a foundational understanding of the problem. Now, when solving these types of problems in interviews, always start by clarifying the graph properties, whether it's directed or undirected, weighted or unweighted.
This ensures you select the appropriate algorithm.
Clearly explain your reasoning throughout the process, justifying why you chose a specific approach.
Finally, always strive to optimize for both time and space complexity.
Testing your solution with edge cases is essential to ensure its correctness and robustness. By following these steps, you can confidently approach minimum spanning tree problems and related variations in interviews.
Great job!
To summarize, we analyzed the problem connecting cities with minimum cost and discussed approaches to solve it.
Key takeaways include the importance of graph algorithms like MST for solving connectivity problems. Continue practicing graph-based problems to enhance your skills.
Thanks for watching, and don't forget to like and subscribe for more problem-solving tutorials.
That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!